electromagnetic induction. We are start with the topic coefficient of coupling between the two circuits. Let's continue with this topic. In previous lecture, we come to this equation and is equal to K square root of L1 L2. So coefficient of coupling between the two circuits. Two circuit means this is the coil number 1. We get the equation M, that means coefficient of mutual inductance M is directly proportional to E to 1. In previous lecture, E to 1 means induced EMF in a coil 2 due to coil 1. So M is directly proportional to E to 1, and again we get the equation E to 1, that means induced EMF is directly proportional to number of turns of the coil. This number of turns of the coil. So we already learned that the self-inductance denoted by capital L. Self-inductance L of this coil depends on number of turns of the coil. If we increase the number of turns of the coil, self-inductance of the coil increases. So we write here L is directly proportional to N square. That means N is directly proportional to square root of L. So if there are two coils, then N1, N2 is directly proportional to L1, L2, or we can write it as square root of L1, L2. See, observe these two steps. M is directly proportional to E to 1 and E to 1 is directly proportional to N2. Now, by observing these two equations, we can replace E to 1 with M. We can replace E to 1 with M, and we get the equation M is directly proportional to M. This M, coefficient of mutual inductance, is directly proportional to N, and we know that N is equal to square root of L. There are two coils, therefore we write here L1, L2. So mutual inductance is directly proportional to L1, L2. That means product of self-inductance of the two coils, or we can say that two circuits. So we get if we remove this symbol, direction symbol, we get M is equal to K into square root of L1, L2. This K is called as a coefficient of coupling between the two circuits. This K is called as a coefficient of coupling. Coefficient of coupling between these two circuits. That means the coupling relation between these interrelation between these two coils or these two circuits. Now this K is called as a coefficient of coupling, and usually this K having a value less than 1 or less than unity. This K having a value less than 1. So if K is equal to 1, this coefficient of coupling is 1, then we get M is equal to square root of L1, L2. Mutual inductance of the two circuits is equal to square root of L1, L2. Now from this equation or from this point, we have taken three cases of these two circuits. First case, if K is greater than 0.5, the value of K, the value of this K is greater than 0.5, then two coils are tightly coupled. Two coils are tightly coupled. When the value of K is greater than 0.5. If the value of K, this value of K is less than 0.5, is less than 0.5, then two coils are loosely coupled with them. Then these two coils are loosely coupled with them. When third case, when L1 is equal to L2, when this L1 is equal to L2, then a coil with itself, that means self inductance L is coupled to itself. When L1 is equal to L2, then this coil is coupled with itself and we call it as a self-inductance. Self-inductance is denoted by capital L. So we get these three values of this coefficient of coupling between these two coils, and we get the value of K as K is greater than 0.5. Second, K is less than 0.5. If L1 is equal to L2, then the value of mutual inductance is changes. Now, when L1 is equal to L2 is equal to L, then we get M is equal to K square root of L multiplied by L. If this K having a value 1, then we get M is equal to square root of L square, and which is equal to M is equal to L. We get M is equal to L. Now M means coefficient of mutual inductance between the two coils is equal to self-inductance L. L means self-inductance of that coil. That means this M is equal to self-inductance of each coil. So when L is equal to L1 is equal to L is equal to L, that means self-inductance of the coil 1 is equal to self-inductance of the coil 2 is same, then we get M is equal to L. If these two coils, coil 1 and coil 2, if these two coils are wound on a common iron core, for example, this is the iron core and these two coils are wound on this iron core. This is the coil number 1 and here is the coil number 2. Then coefficient of coupling between these wires is considered as a unity. This coefficient of coupling between these two coils are considered as the unity. That means the value of coefficient of coupling K is equal to 1 when these two coils are commonly wound on this iron core. For a two air core, for example, in second case, if we use two cores, this is the first core and this is the second core, and each wire is wound on a separate core, like this. coefficient of coupling K depends on the distance between the two coils. For example, this is the coil. Distance between the two coils and the angle between the axis of two coils. Means in second case, if these two coils are wound on a separate iron core, then the value of K depends on distance between two coils and the angle between the axis of core. When these coils are parallel, then the coefficient of coupling is maximum. When these coils are parallel to each other, we get coefficient of coupling is maximum. And if axis of these coils are at right angles, means these two coils are perpendicular to each other, then the value of K means coefficient of coupling is minimum. These 2 points is important. When we get the maximum value of K, when these two coils are parallel to each other, and we get the value of K minimum when these two coils are perpendicular to each other. So this is the value of coefficient of coupling between the two circuits we get, and these are the 3 cases. So next point is transformer. This is the diagram of transformer. This is the primary coil, and this is secondary coil, and this is the iron core. Primary coil, secondary coil. There is a small distance between these two coils, and we know that when the coils are kept in front of each other or kept neighbor to each other, then we found their mutual inductance. And the most important point of the chapter is transformer. The basic principle is based of this transformer is on this mutual inductance. So mutual inductance is the basis. Mutual inductance is the basis of all types of transformer. जेवढे वेगवेगळे टाइप्स ट्रान्सफॉर्मरचे आहेत त्याचं बेसिक जे आहे ते बेसिक कशावरती डिपेंडेंट आहे, म्युच्युअल इंडक्टन्स वरती. आणि हा ट्रान्सफॉर्मर जो आहे तो ट्रान्सफॉर्मर म्हणजे काय असतो, एक आयर्न कोर असतो आणि त्या आयर्न कोर वरती वायर ज्या आहेत त्या वायर्स 2 वायर्स काय केलेले असतात, वाउंड केलेले असतात. फर्स्ट जी वायर आहे त्याला आपण काय म्हणणार आहोत, वायर किंवा कॉईल आहे त्याला आपण काय म्हणणार आहोत, प्रायमरी कॉईल. आणि सेकंड जे आहे त्याला म्हणणार आहोत सेकंडरी कॉईल. या प्रायमरी कॉईलला आपण इनपुट असे म्हणतो. प्रायमरी कॉईलला आपण ट्रान्सफॉर्मरचं इनपुट असे म्हणतो आणि सेकंडरी कॉईल दॅट मीन्स आउटपुट ऑफ द ट्रान्सफॉर्मर. So what is the use of transformer? Transformer is used to change high voltage to low voltage or vice versa. ट्रान्सफॉर्मरच्या साहाय्याने आपण हाय व्होल्टेज जे आहे ते हाय व्होल्टेज लो करू शकतो किंवा लो व्होल्टेज जे आहे ते लो व्होल्टेज हाय व्होल्टेज मध्ये कन्वर्ट करू शकतो. मोस्टली जे काही आपण इलेक्ट्रॉनिक डिव्हाइसेस यूज करतो त्या इलेक्ट्रॉनिक डिव्हाइसेस मध्ये फॉर एक्झाम्पल मोटर असेल किंवा फॅन असेल किंवा आपण जे काही मोबाईल किंवा वेगवेगळे इलेक्ट्रॉनिक डिव्हाइसेस यूज करत असतो त्यामध्ये मोस्टली ट्रान्सफॉर्मर जो आहे तो ट्रान्सफॉर्मर यूज केलेला असतो. सेल फोन्स, लॅपटॉप्स किंवा तुम्ही जे काही व्हिडिओ गेम्स पाहता खेळता आणि पॉवर टूल जे आहे ते पॉवर टूल्स त्याचे ते ट्रान्सफॉर्मरच्या साहाय्याने बिल्टअप केलेले असतात. सो मोस्टली इलेक्ट्रॉनिक डिव्हाइसेसमध्ये आपण ट्रान्सफॉर्मर जो आहे तो ट्रान्सफॉर्मर यूज करतो. So transformer is a device. It is a device. Transformer, it is a device used for changing. I write here used for changing high voltage of alternating current from low value to high value or high value to low value. We can see this transformer by the roadsides in villages and cities. आपण विलेजेस मध्ये किंवा शहरांमध्ये सुद्धा मोठमोठे ट्रान्सफॉर्मर जे आहेत ते ट्रान्सफॉर्मर आपण लावलेले पाहतो. इलेक्ट्रिक्स जे काही खांब्स हे असतात, पोल्स असतात, त्या पोल्सवरती ते ट्रान्सफॉर्मर जे आहे ते ट्रान्सफॉर्मर आपण पाहतो. रस्त्याच्या कडेने शक्यतो असतात ते. सो व्हेनेवर व्हॉट इज द वर्किंग, नाउ वी आर गोइंग टू सी द वर्किंग ऑफ दिस ट्रान्सफॉर्मर. सो व्हेनेवर द magnetic flux linked with the coil changes, and EMF is induced in the neighboring coil. This is the basic principle of mutual inductance. What it is? Whenever the magnetic flux linked with a coil changes and EMF is induced in the neighboring coil. So in the transformer there are two coils. We call it as a primary coil and it is shown by letter P, and secondary coil is denoted by letter S. So in transformer there are two coils, primary and secondary, insulated from each other and wound on a soft iron core as shown in a figure. Now see, this is the one type of transformer. There are two coils, two wires. If we say this is the primary, then it is a secondary. Or when this yellow wire is primary, then this wire act as a secondary. This wire wounds on this iron core. This is the iron core and the winding is inside that iron core. So this is the primary coil as shown in figure, and in this transformer also this is the primary and this is the secondary coil. Primary coil act as a input of this transformer. This primary coil act as a input of the transformer, and this is the secondary coil act as a output of the transformer. Now this primary wire converts high voltage. This is the input, high voltage incoming in this coils, and this secondary coil gives us high voltage of the electronic circuit or of this transformer. So this mostly use of this transformer is changing or converting the voltage of alternating current from low value to high value. So this is the one type of transformer. Now primary coil, I told you that primary coil we call it as a input. This primary coil we call as a input of the transformer, and secondary coil of the transformer we call it as a output of the transformer. When an AC voltage is applied, when an AC voltage is applied to the primary coil, the current through the coil changes in the secondary coil, and this current changes the magnetic flux through the core. This current flowing through coil 1 changes the magnetic flux through this core. As the changes of magnetic flux, magnetic flux is linked both primary and secondary coils, and due to this EMF is induced in each coil. As the magnetic flux of this core changes, and EMF is induced in both the coils. So the magnetic flux linked with coil depends on number of turns in the coil. Magnetic flux we show it with the letter phi. Magnetic flux is directly proportional to number of turns of the coil. So phi is directly proportional to N. As number of turns of the coil increases, magnetic flux of the transformer or of these two coils also changes. So phi is directly proportional to number of turns of the coil. So phi magnetic flux link per turn with both the coils with respect to time t. So NP, capital NP, number of turns of the primary coil, NP and NS. NP and NS be the number of turns of the primary and secondary coil respectively. Number of turns of primary and secondary coil respectively. As this is the transformer, if we increase the number of turns of the coil, the magnetic flux linked with this core increases. So magnetic flux depends on the number of turns of the coil. Here we use two coils, primary and secondary. So number of turns of the primary coil is denoted by NP, and number of turns of the secondary coil is denoted by NS. So NP and NS be the number of turns of the primary and secondary coil respectively. The magnetic flux phi linked with primary coil. Magnetic flux phi linked with primary coil. Linked with primary coil is phi p. Magnetic flux with a primary coil we denote it as phi p. Phi p is equal to n p, number of turns of the primary coil, and magnetic flux linked with it. So we get magnetic flux linking with the primary coil, phi p is equal to np into phi. Similarly, for a secondary coil, we get phi s. That means magnetic flux linked with the secondary coil. Magnetic flux linked with the secondary coil, phi s is equal to ns into phi. Number of turns of the secondary coil into magnetic flux of the coil. So we get phi s is equal to ns into phi. We know that as the magnetic flux link, the EMF is induced in the coil. The EMF is induced in the coil. So induced EMF in primary as well as in secondary coil. Induced EMF in primary and secondary coil is EP is equal to minus d phi p divided by dt. Induced EMF in primary coil EP is equal to minus d phi p divided by dt, and in secondary coil induced EMF ES is equal to minus d phi s divided by dt. So in both the coils we get induced EMF in primary EP is equal to minus d phi p divided by dt, and in secondary coil induced EMF ES is equal to minus d phi s divided by dt. So EP is equal to, we write here, EP is equal to minus d by dt. EP is equal to minus d by dt. We write here phi p is equal to np into phi. Substitute this value of phi p. Magnetic flux linked with the primary coil. So we substitute here np into phi. np into phi. So EP is equal to minus d by dt phi p. Value of phi p is np into phi. So EP is equal to minus np. EP is equal to minus np d phi by dt. EP is equal to minus np d phi by dt. Similarly, in secondary coil, ES, the induced EMF, ES in a secondary coil, ES is equal to minus d by dt, and the value of phi s, we know that value of phi s is equal to ns into pi. Let's substitute this value in this formula, and s into pi. So we get is equal to minus ns d pi by dt. Es is equal to minus ns d pi by dt. This is the induced EMF in a primary coil, and this equation number 2. Equation number 2. Induced EMF in a secondary coil is equal to minus ns, number of turns of the secondary coil, into magnetic flux per unit time. So we get these two equations for two coils, primary and secondary. Now the most important point, if we take a ratio, for an ideal transformer, input power is equal to output power. Input power is equal to output power. So we know that for the power, equation is EP into IP. EP into IP, that means I into phi. I current flowing and phi means voltage, and this voltage we call it as a electromotive force, that means EMF. EMF E into I. Same equation we get for power. Input power is equal to output input, therefore we write here IP. In a primary coil, this is the primary coil. EP into IP is equal to output power, that means output, that means secondary. In a transformer, we get output from this secondary coil. So here we write ES into IS. ES into IS. So ES divided by EP, ES divided by EP is equal to IP is equal to IP divided by IS. We get equation ES divided by EP is equal to IP divided by IS, which is equal to N, which is equal to NS divided by NP. ES divided by EP is equal to, we get NS divided by NP. So we get again an important equation. ES divided by EP is equal to IP divided by IS is equal to NS divided by NP. For an ideal transformer, we get this type of ratio. ES divided by EP is equal to IP divided by IS. IP means current flowing in primary coil, and IS means current flowing in a secondary coil. So we get this important equation about the transformer, and from this equation we have two cases, two important cases. Case 1. When NS, first case, when NS is greater than NP. NS means number of turns of the secondary coil is greater than number of turns of the primary coil. And this is the secondary coil having number of turns more than 3. If this type of transformer, then ES is greater than EP. Induced EMF in secondary coil is transformer when Ns is greater than Np. Number of turn of the secondary coil is greater than number of turn of the primary coil. In that case, Ip, current flowing in a primary coil, is greater than Is. Current flowing in a primary coil is greater than current flowing in a secondary coil. Current in a primary coil is greater than current flowing in a secondary coil, and this type of transformer we call it as a step-up transformer. In second case, when Ns is less than Np, when Ns is less than Np, that means if this coil has a number of turns, primary coil, and secondary coil have a number of turns less than primary coil, Ns is less than Np. This transformer having secondary coil having number of turns is less than primary coil, then Es, then in that case Es is less than Ep. Yes, that means induced EMF in a secondary coil is less than induced EMF in a primary coil, and this type of transformer we call as a step down transformer. This type of transformer we call as a step down transformer, and in step down transformer Ip, that means current flowing in a primary coil, is less than Is. Current flowing in a primary coil is less than current flowing in a secondary coil. So there are mainly two types of transformer: step up transformer and step down transformer. So up to this point the theory is completed of this chapter, electromagnetic induction. So for today we stop here. Thank you.